Hey guys, in this video we're going to talk about two examples related to the concept of conservation of energy. First one is example 11 in your notes packet. Now I realize in the question it's about a Hot Wheels car going around a track with a loop-the-loop. I've drawn a marble though because I have a marble track. I don't happen to have a Hot Wheels track available, and so marbles it is, right? And more or less the questions are, how high do we got to drop it from for it to actually make it around the loop-the-loop? And then, okay, what's the maximum speed when it reaches the bottom? Okay, fine. So let's begin with actually looking at the loop-the-loop in question. Oh, he had it right there. Yeah, yes, I did. All right, so let me pull out a marble here. And as you can see, right, there's a loop-the-loop portion right here. And if I drop it from, all the way at the top, it falls on the floor. As you can see, if I drop it from all the way at the top of the marble track, it makes it around easily. On the other hand, if I drop it from too low, it didn't make it around at all, right? There's a minimum spot that you have to drop it from in order for it to have enough speed that it will be able to make it past the top of the loop-the-loop. Now, you may be thinking to yourself at this point, oh yeah, minimum speed at the top of a loop-the-loop. I remember we talked about that, when was that? Last unit. That's a centrifugal force question, right? There is a minimum speed that it must have to make it around the top of the loop-the-loop by saying that the gravitational force is equal to the centrifugal force. And the value of the normal force is essentially 0 if it's going exactly at the minimum speed. Okay, all right, let me draw a force diagram here in case you're not quite sure. So here we have the marble or car, whatever, at the top of the loop-the-loop. And you would know that if it was going, say, at a greater speed than necessary, there would be a normal force pushing it down, restraining it to move into a circle. All right, now, if it loses contact with the track, that normal force is, of course, 0. And if it's going exactly at the minimum speed where it just barely is brushing the top of the curve, then the normal force is basically 0. And without that normal force in there, the gravitational force equals the centrifugal force of mv squared over r. And now, why do we need this? Well, what this is going to tell us is the minimum speed that it would have to have at the top of the track. And that minimum speed turns out, square root of g times, we're going to say big R because big R is labeled as the radius of the track. Okay, fine. That's not the answer to the question. The question asked was, what's the minimum height that we would have to drop it from in order for it to make it around the loop-the-loop? That is an energy question. So we have forces for one part of the question, but energy for another. That's perfectly permissible. We will do that all the time in physics, where you'll have forces for one part, energy for another part. Happens all the time. All right, now to do this next bit, what we're going to have to do is, well, I don't know, some of the energy stuff. Step 1. Decide that it's an isolated system. In this case, yeah, it's an isolated system. It doesn't explicitly say frictionless, but there's no information given about friction, so we are to presume that there is in fact no friction, because without any information about it, the problem becomes unsolvable. Second, we have to decide what kinds of energy are going to be present at each of the various positions. Now, to do part A, you don't need to care about this spot down here. We only care about the initial position and the final position, right, the top of the loop-the-loop. All right, but I'll go ahead and figure out the types of energy present at all of those locations. Now, remember, there's only ever 3 kinds of energy that you're going to see in mechanics problems. You're going to have kinetic energy, gravitational potential energy, and elastic potential energy. There's no springs in this entire question, so I'll just cross that out in advance. It has this kind if it is anywhere above the lowest point in the problem. So right here at the start, it has definitely gravitational potential energy. at this spot. It's above the lowest point in the problem, so it has also gravitational potential energy. A different amount, okay, because it's at presumably a different height, but it has some amount of gravitational potential energy because it's not at the lowest position. All right, it will not have kinetic energy here. We are to assume that it starts from rest because otherwise the question doesn't make sense. If we gave this an initial push, it could start from anywhere, right? There's no minimum height if we give it a push, right? All right, so no kinetic energy there. It's starting from rest. We just established that there must be some amount of kinetic energy at this position or it wouldn't make it around the loop-the-loop. Okay, and then here at the bottom, only kinetic energy. No gravitational potential energy because that is the lowest position that it can reach during the course of the problem. All right, so now we will start actually plugging things in to my energy equation. Delta, if you recall, means final minus initial. That won't matter so much for this question because it's an isolated system, and therefore the final energy is equal to the initial energy. All right. The final energy. Well, for this question, it's starting there, and this is the moment that we are considering final. And so we will say UG plus K for that moment. E initial, that's this moment. We will say UG, and then to maybe distinguish this UG from that UG, I'm going to call this one UG initial. All right, now I got you this far. You should probably pause me and try and see what you can come up with on your own, right? We've already done a lot of stuff with the forces. We've got the basic energy set up. Pause me, see what you can do on your own. No, really, pause me. Okay, now that you have resumed the video, UG initial is, well, all right, the formula for it is mgh, and h is what you're trying to solve for. So I'm not going to plug anything in for it. That's the h that I'm trying to solve for, is that h min for minimum height. The UG over here is, well, okay, mgh is still the formula, but you actually know what this height is. What do you mean, Mr. Erickel? This is a symbolic problem. I don't know what the height is. Read the prompt. The prompt says, determine the minimum height in terms of the radius of the circle. In terms of the radius of the circle. You can express the height that this is above the lowest point in terms of the radius of the circle. It is 2 radii, or 1 diameter, above the bottom. So when I say mgh, this h is 2 times r. All right, and then our formula for kinetic energy is 1/2 mv squared. The v that you're going to plug in there is the one that we worked out. This one. You already know the speed that it would have to have at the top. Now, had we not remembered about forces and how the centrifugal force can help me figure out the minimum speed at the top of the loop-the-loop, this actually would be an unsolvable question. You couldn't do it only with energy. Energy can't tell you the speed that this would have to have in order to not fall off the track. It could only tell you how fast it would be going there, given that you knew like where it started from, which is not what you're being asked to do. You're being asked to figure out where to start it from, given that it just barely makes it around. Okay, so we'll plug in this for my v, and this is what the line below it would say, mg times 2r. This, by the way, could be written as 2mgr, and that's maybe actually how I ought to write it, instead of leaving that 2 buried in the middle. That's just silly. Why would I do that? Okay, so 2mgr minus, plus 1/2 m. All right, here's my v, and it's squared, which undoes the square root, and then equals mgh min that I'm trying to solve for. All right, Let's see. All right, a little bit of algebra later. That you see that there's an m in every single term, so the m's will cancel. You see also that there's a g in every single term, so the g's will cancel. That leaves me with 2r plus 1/2 r equals h min. All right, now if you were to look at the answer key, you would see that it says 5/2 r. That's just 2 plus 1/2. 2 plus 1/2 is 5/2. Or you could express the answer honestly as 2.5, and that would also be perfectly acceptable. But very often symbolic problems are going to tend to have answers that are expressed as fractions. So I will keep with tradition here and say 5/2 r. All right, let's take a look at the next part of this question. They want to know the maximum speed. All right, now the prompt didn't actually say find the speed at the bottom, but you probably could guess from experience that the maximum speed will occur when it reaches the bottom. Okay, all right. And since it's a frictionless track, it doesn't matter whether we're talking about the first time it's at the bottom or the second time that it's at the bottom. It's just the same speed because no energy is being lost due to friction. Same basic setup. All right. That means since it's still frictionless, that the final energy and the initial energy are equal. The initial energy is still UG. The final energy in this case, since we're talking about not the top anymore, but the bottom, is just K. All right, so now we've got 1/2 mv squared equals mgh, and we have an expression for h from our previous work. Also notice that the m's cancel out. Since it's in every term, I'll go ahead and just cancel that out. Now we have g times 5r over 2. Okay, a little bit of algebra later. You should get that the factor of 2 will cancel from either side, and the speed when it reaches the bottom is the square root of 5 times gr. Beautiful. Put a box around it. That is the answer. Yay. All right, next up we're going to look at example 12. I'll try and treat this one very quickly. In example 12, it says we've got a bowling ball. We're dropping it onto a spring. The spring compresses some distance, and we're supposed to figure out what that distance is based on the other information they've given us. All right, now, I'm not going to spend a ton of time looking at this because, frankly, I'm not going to grind through the algebra. What this problem needs is a good diagram, and this is a good diagram for it. So you can copy that down, and then pause me, see what you can get done on your own, right? Pause it, try it out, see if you can come up with the correct answer. If you can't, then resume the video and see where you may have gone wrong. All right, so here goes. What kind of energy does it start with at the top? Well, all right, obviously, gravitational potential energy. You are correct. What kind of energy does it end up with here at the bottom? Well, so the way that this question goes, for a lot of people, they imagine they've got to like figure out the speed when it hits the spring. No, you don't need to know that. It doesn't actually matter. You can still say this is the beginning, this is the end, and here at the end, there's no kinetic energy, right? That's the bottom of the bowling ball's motion because it has hit the spring and compressed it as far down as it can. It's the bottom because it stops there. Therefore, there's no kinetic energy at the lowest position, only elastic potential energy. All right, we're also, in this case, once again allowed to assume that there is no change in energy for the system. It's just changed forms from one type of potential energy to another one. No work has been done by friction because we're assuming that air resistance is negligible. So the problem actually ends up being as simple as this, and yet a lot of the time people get the wrong answer. All right, the reason they get the wrong answer is because of the following reason. When they plug in for the gravitational potential energy, they imagine that when it says MGH, that H is D. All right, now take another look at the picture and see if you agree with that assessment still. What you should see is that the bottom of the bowling ball has gone from being here to there. That means that the H you should be using isn't D, it's actually D plus X. All right, now I said I'm not going to work through the algebra for this so much. All I'm really going to do is plug in that last one and then say from here you should be using distributive property and probably plugging in numbers. And then once you've got all the numbers plugged in, you should note, oh hey, it's got an x squared in it. It's also got a regular x, and then I've got some constant. I wonder where I've seen that. It's a quadratic. So you should use the quadratic equation or polysimult on your calculator, which will give you the answer with like a minimum of fuss and bother. All right, there are two answers. Pick the positive answer since it's a distance that's been compressed. All right, hope that helps, and I hope to see you guys in class soon. Thanks.